due to various reasons. We decided not to discriminate against anybody, and I think it's a good thing that we can have remote talks. It turns out that in the previous remote talks worked out pretty well. We got a good portion of participants who joined us remotely. So today in the morning, before coffee break, we'll have 2 remote talks about future facilities. And the first talk will be about LHeC, the second talk will be about EEP. And the first talk is going to be given by Paul Newman, whose title you see there, the Large Hadron Electron Collider. Okay, so Paul, you may start, and I'll give you 10 and 5-minute warning. In total, 40 minutes, and then discussion.
Okay, thank you. Do you hear me okay?
Yes.
Good, thank you. Okay, well, thank you very much for the invitation, and apologies that I can't be there. It's 5 p.m. here, and I've just done 3 hours of tutorials and a lecture, so it's been busy teaching time. So I was asked to talk about the LHeC, which is probably not new to many of you, but I'll try and do so, and with a focus on the physics prospects for the whole thing. So just to start though with a bit of context, so this famous or infamous plot by now shows various EP past, present and future facilities in a plane of luminosity versus centre of mass energy, and the green stuff at the top is LHeC. So that's based on adding a 60 GeV electron accelerator to the CERN LHC complex at a luminosity of 10 to the 34 per centimetre squared per second, which could, in principle, run simultaneously with ATLAS and CMS in the high luminosity phase of the LHC. So compared with HERA, the previous only collider that we've had, there is an increase in centre of mass energy into the TeV range, but the probably much more important and fundamental thing is the increase in the luminosity by several orders of magnitude. And that takes you into the similar sort of region to the EIC machines, but with higher energy. There is another project. If anybody has the will to live and wait around long enough for CERN to build its next tunnel, the idea is that there'll be a future circular collider with 50 TeV proton beams. So that's this thing at even higher centre of mass energy, but comparable luminosity, which is the EP version of FCC. Okay, so all of that, or some of that at least, appears in the conceptual design report, which is by now 6 years old. And I've written here, is this fake news? In a way it is, because a lot has changed since that was published. So some of what I'll share will be from the CDR, but a lot of it will be new. So very quickly on how the design works. I mean, the basic parameters are defined by a constraint that was given to the project by CERN in the first instance, which is that the power consumption should be 100 megawatts maximum. And that's what drives you to the electron energy of 60 GeV. And it's a question of what sort of luminosity you can get out of that sort of power. And the way to make it as large as 10 to the 34 is to use an energy recovery LINAC setup. So I say it's LINACs, it appears in this racetrack formation where you actually go around 3 times, going through 10 GeV LINAC accelerating structures 3 times each before interacting with the LHC, and then actually winding the electron back down through the same structures in order to recover the energy. So the accelerating voltage gradients and so on are relatively modest. The big challenge in all of that is obviously the energy recovery. But on paper, at least, you can get something approaching 100 inverse femtobarns per year. So we end up thinking about an inverse attobarn total amount if you could run for 10 years with this sort of configuration. Just to say that, I mean, nuclei are very much part of the design as well, including deuterons. So there is also a design where you put heavy ions and deuterons into this with more modest luminosities, obviously, but that's also very much part of the study. So when could this happen is the obvious question, and it's not an easy one to answer because there's, this doesn't sit as yet in any of the CERN planning. But this plot here basically shows the future of the LHC, and all of the LS's stand for long shutdown. So LS3 is the really big long shutdown where the machine gets upgraded to the high luminosity LHC, and you can see the increase in luminosity after that. So the idea would be for the LHeC to run alongside the existing LHC experiments in this high luminosity LHC period, which runs for, on paper at least, I mean, this is a little bit out of date, this plot. On paper, this runs from about 2026 to 2040 with multiple shutdowns in the middle. So, you know, there may, if CERN at some point decides that this is part of its future program, there may be opportunities to put the LHeC in sometime in the 2030s. But I emphasize that none of that's approved yet. Where could you put it? So this picture just shows the LHC is the big ring there. Point 1 is Atlas, point 2 is Alice, and point 8 is LHCb. So there are designs in which the LHEC is added at point 8 or point 2. Point 2, which is Alice, is certainly the favourite, that at some point the Alice program would end and the LHEC might go in instead. There are various different sort of sketches of what happens on here. The 1, 3, 1, 4, and 1, 5 is just how many times the electrons go round for every time that the proton goes around the LHC ring, so you have to synchronise that. And how big it is a compromise between the sort of tunnelling costs, the magnet costs, and the various infrastructure. 60 GeV is the yellow ring that's shown there, and nominally based on the Alice site. So there's a quick overview of the physics program. I certainly like to think of it as being complementary to what the aims of the EIC are. So I mean, if you ask the LHEC people what their top physics priority would be, they would probably say it's a standalone Higgs program. There's then also a BSM program. There's a very impressive parton density extracting program, which also relates to the LHC discovery potential, and I'll talk about that a little bit later on. All of that is being written up as part of the European strategy exercise at the moment, and we see whether Europe sees that as being valuable enough to include in its future program. There is, of course, also a LHeC and a QCD program and a heavy ion program as well, which overlaps more with the electron ion collider. What the LHEC doesn't do is provide polarized targets. So there's no way that we can polarize the protons at the LHC. So that's one thing that really would remain unique to the EIC if both of these things happened. Just a word on kinematics before I get into the physics. I mean, the design of this thing crucially depends, has a crucial requirement on acceptance, essentially. So the top right-hand plot here is basically the same as I showed in the last, the same kinematic plane as I had on the last page, but with a blow-up now of the low X region, and just showing lines of constant electron scattering angle. And if your electron if your detector only goes to within 10 degrees of the beam pipe, so that you only see electron scattering angles up to 170 degrees, you basically lose your entire low X physics program. You only have the stuff in the nose at the top there. Whereas if you build a detector that goes within 1 degree of the beam pipe, you essentially see the whole kinematic plane above q squared of 1, which I think is a very good thing to aim at. So the design of the detector is all based around that. There are similar arguments for the outgoing proton, that you need to reconstruct the hadrons very well up to close to the beam pipe in order to get good resolution on high X. Just a couple more arguments on acceptance for some other processes. So at the top there is what happens in elastic J-psi production, where the direction that the muons from the J-psi decay go depends crucially on the W, the photon-proton center of mass energy in the event. And once again, there's a contrast there between a 1 degree detector and a 10 degree detector that shows that you basically lose your whole high energy program if you don't capture muons down to really quite close to the beam pipe. There are similar arguments as you might expect throughout the whole physics program. There's just one more here on Higgs acceptance, but I think the point is probably clear. So on the detector, so there's a fairly detailed detector design, which I'm going to only skim through very quickly here. The detector technologies are basically, the aim is to use technologies which are already achievable rather than that require lots of R&D, and for the most part that's what's in. That's fairly easy to do at the LHC because, the condition, people have designed complicated detectors for very high radiation environments for Atlas and CMS, and the requirements here are substantially less demanding than that. So, there's tiny fractions of the HL-LHC radiation fluence, and the pileup, so the number of interactions per bunch crossing, which is 200 per bunch crossing at the HL-LHC, is only about 0.1 for this machine. So it's comparatively easy, and it can be based on things that have already been done at the LHC. But with some flexibility to change, of course, as time goes on. So there was a costing of the detector for the CDR, which is about 100 million Swiss francs core cost. So core cost is CERN language for just the capital cost. You have to multiply by a factor for people. Okay, so just for the record, there's a picture of the detector that was for the LHeC for the conceptual design report. It's relatively compact. It's smaller than any of the LHC detectors. One feature to point out is these discs in the tracking region, these red discs, which are designed to capture electrons coming out, so that anything coming out within 1 degree hits at least 2 of these discs. Otherwise, it looks like I could talk through the technologies, but it's probably not that relevant to us. There's what happens if you go to the FCC. So this is the CERN Future machine. Basically, everything scales up by a factor of about log of the center of mass energy. So it's about a factor of 2. So the detector gets about a factor of 2 bigger. But in order to keep these 1 degree electrons being within the acceptance, you now have a crazy long series of silicon disk detectors with 5 in the backward direction and something like 8 in the forward. Okay, so I was going to spend the rest of the talk talking about physics, starting with parton density constraints. So there have been a few studies of this, and I just picked a few plots at random, which may be a little bit out of date. The game here is that you make a full simulation of of LHeC data, so charged and neutral current, deep and elastic scattering, and then you sort of put it through the standard fitting technology, which in the case of the 2 top plots here was here a PDF, actually an old version of it, but it gives a nice picture of the sort of improvements that you get. This is relative uncertainties on the gluon on the left and the C on the right, just showing that going from what HERA, the outer envelope, which is what HERA achieves, add a bit of LHC data and it doesn't have that much of an impact, and the innermost bands are what happen if you fit HERA data plus LHeC. So you get really very tight constraints to a couple of % up to the very highest X in both the gluon and the C. And there's another plot in the bottom right there, which is just the impact that you could have on one of our old problems, which is what happens to the D over U ratio as X tends to 1, showing some existing PDF sets, how they explode in their predictions for this ratio above about 0.5, and the LHeC band, which would resolve it. So there are many such examples of PDF studies like that, which come together with a very precise per mil level experimental determination of alpha S. You don't just get the C quarks and the gluons though. This thing gives you a full flavor decomposition, and this is just a plot to show how the cross sections in EP for various different heavy flavor processes vary with the lepton energy, vary with the center of mass energy essentially. So you can see very high rates for all of these things, beauty and charm and so on. But also, I won't talk about top quark physics, but there are, literally hundreds of thousands of top quarks being produced in this facility per year on paper. So you can really do detailed top property studies and things like that as well. So one or two of the more detailed studies of flavor decomposition for all of this are just put in on this slide. So this is now just creating pseudo data, looking at what sort of precision you could get on data points and in what kinematics. For F2 beauty on the top right, so that's basically the contribution to the structure function from beauty quarks. So you see wonderful measurements. There's some HERA points put on there for reference, but going down to 10 to the minus 5 or below, so beauty becoming a low X observable. The bottom right example is for strange density tagging by using outcoming charm quarks in charge currents. So that's just a couple of examples of how you start to constrain the flavor decomposition in these measurements. Okay, so why should we care? So to this community, probably I don't have to justify this, but to an LHC-based community, it's often important to explain why they need to care about PDFs. So there's just a couple of examples here from the LHC, which show how LHC physics starts to become limited by our knowledge of the parton densities at high X. So what basically happens is that if you search for some sort of new physics where you don't have a nice, neat bump, like, you know, Higgs to gamma gamma or something, but you have a deviation from expected cross sections, then of course, if you no longer know the predicted cross section very well, then you can't discover the new physics. And there's a couple of examples on here. On the right hand side, this is gluino production from a diagram like this one, which basically shows how the PDF predictions just diverge rapidly when you get to above a mass, an invariant mass of that of about 2 TeV. So that sort of sets a fundamental limit on what sort of what sensitivity to gluinos you could have at the LHC coming from PDF knowledge at high X. And the red band in the middle shows what happens if you add LHeC data. You certainly solve that problem. Another example is the W boson recurrences. So if you go to high masses and look for W plus or minus heavier versions of W's, then you have a similar sort of problem, because you don't get bumps because you're either looking in a lepton plus a neutrino, or you're looking in two jets. And once again, you know, it's about finding deviations from predictions rather than bumps. And already Atlas is limited at about 5 TeV for these things by the PDFs at high X. So LHeC isn't on there, but it sort of demonstrates the point. So in the context of this European strategy exercise that I briefly mentioned already, there is an effort to try to work out how well we can know PDFs in the future for the LHC. And there's a nice, this is work in progress, but I thought I'd include it anyway, because I think it really illustrates the point. Basically, there's luminosities for producing, or uncertainties on the luminosity for producing new particles from two gluons on the top and from a Q-bar resonance on the bottom. And if you look at the left-hand plots first, the green is basically what we know at the moment. So this is the uncertainty blowing up when you get to above about a TeV or so. And then there are some estimates of what you can get by adding different types of data from the LHC, first of all, on the left-hand side. So it's asking the question, can the LHC solve its own problems about high-X PDFs and so on? And one answer to why that's not true is here, really, that the level of improvement, okay, depending on your assumption about systematics, you're somewhere between the red and the blue hatched bands, but basically the problem's still there. Whereas on the right-hand side, if you take the current data and add the projected LHeC data, then basically it's transformationally different. And apart from the very highest X, the problem's completely solved. So that's work in progress, which is hopefully going to converge soon, but tells the story. So let me talk a bit about Higgs production, since, as I mentioned, that's probably the main target for this sort of stuff. So the Higgs production modes in EP look like this diagram here. So the highest cross-section is WW fusion to make a Higgs boson. So that looks like a charge current deep inelastic scattering interaction. The subleading process, the next highest, is the same thing, but where you've got ZZ goes to Higgs. So the nice thing about that is you've got two production mechanisms, and you can straight away tell the difference between them, because it's whether you get a neutrino or an electron at the top of the diagram, so you can distinguish. And then the Higgs, of course, can decay to anything. And it's a fairly simple matter to just work out what the cross sections are, and then the Higgs branching decays, and to sort of work out how many events you expect in an inverse Autobahn. And that's summarized in the table at the top of this page here. So charged and neutral current at the LHeC are the two white panels, and then there's another one for the higher FCC version, the longer one. So you can straight away see there's 100,000 odd Higgs to B bar going down the list to maybe 50 Higgs to mu and so on. So those are the sorts of levels. So people have started studying this in quite some detail. There's just one example plot on the bottom there from a study of Higgs to BB bar, where they've done a complete analysis with a simulated LHC, using the sort of generic simulation of an LHC detector to put in all of the backgrounds and work out that this sort of signal here is on a signal to background ratio of possibly as good as 2, which is unheard of in LHC Higgs physics. So that leads you to the conclusion that with an inverse Atterbarn on something like Higgs to BB bar, you could be at the sub% level of precision. And then, so just one more slide on that. This is just a summary of where we think we are with Higgs constraints at the LHeC. I mean, nobody would have thought that EP would compete here, but it turns out that it does. First of all, at the top, this is just simulations of different versions of the LHeC, the sort of precision, relative precision it can get on couplings. So the blue is LHeC, the orange is a version of LHeC based on new magnets in the LHC, the so-called high energy LHC. So that'd just be double the magnet energy, and the green is the FCC version. But I think if you just focus on LHeC, you see the sort of percent level BB bar. Because the WW production mechanism dominates, sub% level on the WW, and then some other channels that you contribute to as well. So that already looks exciting. And if you start to compare it with the with the other machines, probably the plot in the bottom right is a nice one to start with. I mean, you don't beat linear electron-positron colliders. I think that's the first thing to say. Those are sold as Higgs factories, and they do the job, the name as it says on the tin. But you're not far away for some of these channels. And for WW, for example, you're very close. So I think EP and LHeC has to start being taken seriously as a way of studying Higgs physics in the future. And of course, if you could do all of E plus E minus EP and proton-proton, you'd get to the ultimate precision. So that was Higgs. I'm no expert on BSM physics, and I could try to put some slides together, but I think it's probably not the most interesting thing to talk about here at an INT meeting. So that's just a sort of placeholder where there's a compilation of 50 papers there that have been written on beyond the standard model physics at an LHeC, which I don't plan to go into, but if you're interested, have a look. Good. So I was going to spend most of the rest of the time on LHeC physics. So these kinematic planes here basically show the same XQ² kinematic plane, but on here is an old version of a saturation model. So this is the Golet-Bernat-Wüsthof original dipole model, which shows where the critical line, the saturation curve, is on the plane of EP on the left and EA on the right. So illustrating, first of all, that there is some phase space for both of those below the purple line, where LHeC could see the saturation region in this model in a perturbative regime where Q² is bigger than 1. Although it has to be said that for EP, it still remains pretty marginal. I mean, you've not got very much phase space for that. So there's a message in that in itself, that you really need EP and EA and or multiple different observables to see new physics there. So what's the physics of LHeC? So most of what we know already comes from HERA. The neutral current process that's illustrated on here is I kind of like as a way of thinking about it, because gluons split to QQ bar, and in a very naive approximation, then if you want to know the gluon at 2x, then you need to have some lever arm to see the scaling violations of F2 at a factor of 2 lower x. So that's how HERA sort of leads us to the plot in the bottom right, which is the final word from HERA for PDFs. From HERA to PDF 2.0, where you see really beautiful precision, the result of 15-20 years of work. Beautiful precision on the valence and the height, the C and the gluon, down to about 10 to the minus 3, but with a deteriorating precision as you go to 10 to the minus 4 or below. And that's just simply kinematics. If you want to understand what happens below 10 to the minus 4, you need to go to higher energy. Was there any evidence for saturation in HERA physics? I would say the jury is still a little bit out on that. So there's a beautiful phrasing in the final HERA 2 paper that says there is some tension in the fit between the low and medium Q-squared data, which is not attributable to any particular X region. So that's visible in the chi-squared per degree of freedom going up when you lower the minimum Q-squared in your QCD fit, to show that something is happening in this low Q-squared region. So the text says that it's not particularly any X region, although it then goes on to note that there is a kinematic correlation. So something is happening down there. Could it be to do with saturation, density effects, and so on? There's been interesting new work on that recently, where people have put next to leading log resummation, so BFKL essentially, into these fits, and then the chi-squared per degree of freedom as a function essentially of something similar to Q-squared min. Actually, they're diagonal cuts rather than just Q-squared min. But you can see that if you take the versions where you've got the BFKL contribution in as well, this chi-squared per degree of freedom remains fairly constant down to lower and lower X. So maybe it's just about low X resummation. In any case, I think the final verdict from here, at least in my perspective, would be that there's no firm conclusion on whether or not there's anything like nonlinear dynamics in the low X low Q squared corner at HERA. And if there is, then we don't know much about what those dynamics look like. So enter the LHeC. This is just one set of simulations, actually quite old, from the CDR 6 years ago, which just shows the sort of precision at 1 Q-squared value on F2 on the left and FL on the right. So the big yellow envelopes was an early version of NNPDF. So this is just the full degree of flexibility in DGLAP fits, showing that the precision is way inside that. And also in different nonlinear approaches, either econolised scatterings or color glass condensate, not only do you distinguish between, not only do you identify saturation, but you can distinguish between different models of it. So that looks nice in principle, but then the obvious question is, can you hide away the new effects in the starting parameterizations of the PDFs? So there are some nice studies of that. I think the study is nicer than the plot that I show here, but basically what's been done here is that we've simulated F2 and FL LHeC data using a model that contains saturation, quite an old model, Shore 04. So those are the red points here, and then we've used standard next to leading order DGLAP fits to try and see if we can fit it. Just to see if you can make the saturation effect disappear in terms of what comes out, how you parameterize the PDFs. And the red points was the best fit. So you get quite close with F2 and it breaks with FL. So I think what's going on in the underlying dynamics is that you've got two separate gluon sensitive observables. One is the Q squared derivative of F2, and the other one is FL, and they're in conflict with one another. And that would be the sort of smoking gun that you'd hope to see to establish saturation. So it doesn't have to be inclusive variables, doesn't have to be F2 and FL. You can see similar things if you use charm data. You can also see similar things if you compare what happens in EP with EA. But that's the basic message. So a few words then about exclusive and diffractive channels at low X. So by way of a very quick motivation, a couple of reasons why these might be more interesting for low X dynamics than the inclusive variables. One is that they're sensitive in some zeroth order parameterization to the gluon squared rather than just the gluon. The other being that you have this variable T, which is conjugate to the impact parameter, so that you can essentially scan across the radius of the proton and distinguishing us maybe a central black spot from less dense outer regions, maybe even seeing hotspot type dynamics. So you've got two extra handles there. So we've done a few studies of this. The one that I liked most was elastic Jabe Psi photo production. So it's nice because of the reasons I just gave, but also because of the kinematics with the Jabe Psi. So, relatively simple wave function, the way it decays to, and a very clean experimental signature of decaying to 2 leptons. But also if you take, and this is an example of what scale is taken in Martin Riskin Teubner, for their J psi model. If it's q squared plus m squared over 4, then you're just about in the perturbative region at q squared of 3, and the x values take you nicely down to 5 times 10 to the minus 6, as I put there. So it's a promising process. We simulated it with the standard tools that we used at HERA that maybe are a little bit out of date by now. We assumed a detector with 1 degree acceptance, and then after that we basically assumed similar methods to H1 and Zeus. So the next slide shows, okay, this has been shown far too many times really, and it's certainly something that I got excited about to start with. So it's the cross-section inclusive photo production of J psi's, sorry, exclusive, as a function of the centre of mass energy. The green points here are simulated LHeC data. You can see how those expand out from the HERA data in the bottom left-hand corner. And the purple lines are different centre of mass energies. So realistically, it stops somewhere around about E of 50. And we got excited because it compares sort of 2 versions of the BSAT model, one with a single pomeron and one that's aconalized, and you see a huge effect. So is this a smoking gun signature for saturation? Well, I think you have to be a little bit careful. First of all, because I think the straw man, beware unrealistic non-saturation straw men, I once saw on some slides from Thomas, and I think I agree with him. The 1 pomeron model is not realistic. It doesn't even fit the HERA data, and I think things are a bit more subtle than that if you really want to see things. There is also another issue, which is that the LHeC has started to address this in ultra-peripheral collision physics. So, for example, LHeC-B already has data that go to a higher centre of mass energy than LHeC would manage. So it's not as simple as making that sort of plot, but maybe there are still ways in. So if you go to the T dependencies, so in this plot, this shows the W dependence in lots of different bins of T. So potentially, you know, the way that saturation kicks in could be a function of T because of that conjugality to the impact parameter. So you might see something happening as a function of T. So that's just an illustration of the sort of data that we get there. The other extra handle that we have, of course, is the heavy ions. And if you look at simulations of, I think on the left-hand side, just coherent J psi production off nuclei, you see huge effects between the non-saturated and the saturated versions. The big challenge there is separating out the coherent from the nucleon dissociation or the incoherent version. So you can see on the right-hand side just how the thank you for the time. You can see on the right-hand side just how the breakup lies, like sort of swamps the signal. So the work there is to make sure you can tag nucleon remnants with your ZDC, and that looks promising. But I think between the inclusive measurement, the T dependence, the Q squared dependence, and the heavy ions versus protons, there's still a very interesting program there. I put a slide in on DVCS just to show that it's there and it's been thought of. I think there's a potentially huge program at the LHeC with this, and we haven't really scratched the surface of studying it. All we've done so far is look at inclusive cross sections and said, oh yeah, we can get some nice precision up to high Q squared of almost TeV squared. Looking at X values that are complementary to the sort of thing that's done in TMD physics and so on. We're looking at X values of 10 to the minus 3 down to 10 to the minus 5. What hasn't been done is to look at things like beam charge asymmetries and to see how the sensitivity to GPDs is. So I think that's sort of a placeholder with work that might be nice to do at some point. So then my last topic was inclusive diffraction. So I now, rather than talking about exclusive production of vector mesons, I talk about the sort of diagram in the top left-hand corner up here. So this is now a case where you can produce any system X with a continuum of masses. And the kinematic planes, they get a bit confusing at this point, but they're shown up here on the top right. So probably the proton 7,000 times the electron 60 is the basic LHeC design, which shows you in, just for the case here, what for X pomeron of 10 to the minus 2 you can do in the beta Q squared plane, where X pomeron is the fractional energy loss of the proton. So there's all sorts of physics that lies in this sort of stuff. I suppose the interesting thing about going to LHeC kinematics is that you can start to produce very large massive systems X here for the hadronic system. So just a quick word on that. So I put in the top left-hand corner of this slide, I grabbed this straight from my DIS talk in Kobe, actually. But at that point in time, there'd been a paper that had just come out on this, which is dye-jet production in deep inelastic scattering, diffractive deep inelastic scattering to next to leading order in QCD. So if people are going to that level of trouble in theory, then somehow we deserve some data that matches it. If you do diffractive dye-jet physics at HERA, and that's the sort of diagram in the top right-hand corner up here, you know, we've done this quite a lot, but the limited phase space to produce that hadronic system limits the jet masses to a few GeV, to be honest. So then you know, you can do it, but the jets are fairly low energy, and it makes the physics and the interpretation rather difficult. So there's a nice first plot on the bottom right there of the sort of measurement that we might expect in diffractive DIS of dye jets at an LHeC, and it goes out to 50 GeV or so in the jet PT, which is, I think, a very different sort of thing when it comes to comparing data with theory, where you can expect sub 10% level of comparisons. The bottom left-hand plot there is just the total yields as a function of mx at LHeC. So you can see you can produce diffractive systems with masses up to about 250 GeV. And if I go to the next slide, which just has a back of an envelope calculation of what happens if you go to the FCC, then you can have about another factor of 3. So that's dye jets. Really last topic then is diffractive PDFs. So this was a big success at HERA, where for the first time we managed to extract the diffractive contribution to the proton structure function and express it in terms of quark and gluon densities conditional upon there being an intact final state proton. So this is the top plot was an H1 measurement in terms of gluons and singlet quarks in the Pomeron, if you wish to use Pomeron language, and the bottom plot was the equivalent sort of thing from Zeus, actually this time including jets. So what we've now done with LHeC is to repeat that sort of analysis. We've made LHeC pseudo data, and we've started to fit it with the same technology in order to see what sort of precision and kinematic range we could get on diffractive PDFs and LHeC. So this slide just gives an indication of the sort of kinematic ranges that we've looked at and where the data are. The bottom right-hand corner triangle is HERA data. Thank you, 5 minutes. And then there's a green region here, which is the LHeC kinematics, and a blue, which is the FCC. So separate studies have been done for those two cases, and basically assuming 4 bins per decade in everything, which is about what we got at the LHE at HERA, we've managed to produce pseudo data and to go and fit it. That's the pseudo data. It's crazy. So we used to have trouble presenting this at HERA already, and it's even worse. But every single one of these little panels is the beta dependence of diffraction at a specific Q squared, and the individual panels are different psi values or different X-Pomeron values. So going up to 10% of the proton energy being lost at the top end there, and the bottom end being 2 times 10 to the minus 7. So with some reasonable assumptions about systematics and so on, similarly to similar, not beyond really what was achieved at HERA, we put that into the fitting technology. And this is again work in progress, but here's an indication of the sort of precision we could get. The top plots compare HERA precision on gluons and singlet quarks with the blue region, which is a simulation for LHeC, and the purple, which is if you go to the full FCC. There's a zoom in the bottom, which takes the HERA stuff out just to show you the sort of precision you can get. So depending on your momentum fraction, diffractive parton densities for the gluon between about 2 and 6% precision over a region between 10 to the minus 5 and 10 to the minus 2 in X. And the quark's a bit better than that. So that can be done with very modest luminosity. So that would be a nice first result. Okay, final topic. Sorry, I said the last one was the final topic. I forgot, but I just want to say a quick word on putting a dedicated word on putting heavy ions in. There's the kinematic plane here for EA. Clearly, there's never been an electron-ion colliding beam configuration yet, so it's not surprising that you get something like four orders of magnitude improvement in either x at fixed q squared or q squared at fixed x. And there's all sorts of physics that you can do with that. Just to give one example, so this is on the top some pseudo data for the ratio of the heavy ion F2 to the proton F2 appropriately scaled, which is being fitted with a technology which is based on here a PDF. And the bottom plot here shows the relative uncertainty on the nuclear modification ratio, essentially for the gluon. So the big grey area here just shows what EPPS 2016, so standard nuclear PDF fit, has, and then the black and green and red lines in the middle are different versions of LHeC or FCCEH. So over a very wide kinematic range, down to 10 to the minus 4 or so, you completely nail this, and of course the precision decreases at high X and so on. Okay, so I won't dwell on this, just to say that there is a, the step towards realization of LHeC from a technical point of view is demonstrating the energy recovery LINACs. So there is a program to try and do this actually at LHeC in Paris, where we build, rather than a 10 GeV proton accelerating structures, 80 MeV, but again based on the same RF cavities that were built at JLab. So the idea would be to sort of build something like this at LHeC, firstly as a prototype for LHeC, and secondly for its own standalone physics. There is a cavern at LHeC. It doesn't have much in it except a crane, but some space has been opened up. The plot on the top left, I think, just demonstrates how far there is to go and how important it is to have this prototype. So this is energy against current for energy recovery LINACs. There's only one operating at the moment. These things have been demonstrated up to about 1 megawatt, which looks like a diagonal line in this plot. Perla, which is the LHeC version, takes you to 10 megawatts. LHeC is right up here between 100 megawatts and a gigawatt. So it really is the limiting thing that needs to be demonstrated, and it's where a lot of the technical effort is at the moment. Okay, so I've finished. Just to summarize, so there was a lot happened since the 2012 CDR. The CDR was based on lower luminosities, so the fact that we could get to 10 to the 34 changes a few things. It opens up a Higgs discovery program and maybe searches for new physics. The fact that the LHC starts to become PDF limited also gives another motivation for this as part of a CERN sort of complex. Although, like people in the room over there, my interest is more in the QCD and the low X. So the next goals, we have a European strategy exercise which is ongoing, so we prepare some input for that, and that will be absolutely crucial to this project. I think it needs to be positively cited in the upcoming European strategy exercise to have a chance of going forward. In the meantime, we move towards a TDR, technical design, for the Pearl project. And of course, we further develop the detector and the physics for all of this. Thank you.
Thank you, Paul. Questions or comments? Yes. Probably he can't hear you, but it's better separate.
Hi, Paul.
Hi, Rick.
So if you're optimistic and say that you get a sort of a good reception at this European strategy, so what would be the time scale for this project, you think? I guess it doesn't make sense unless you can run sort of 10 years at high luminosity LHC. Right?
So there are various scenarios, aren't there? I mean, 10 years in parallel with high luminosity LHC would be nice. That's the sort of those are the parameters that we use in evaluating the physics at the moment. But that, as you probably are intimating, means you start around about 2030, which is plausible, but it's quite soon. There are other scenarios where you run partly in parallel with LHC and then continue a bit afterwards as well. I mean, personally, I think the answer is, not before the late 2020s. 2030 would already be optimistic. It basically needs CERN to make a decision that it fits in as a cost, a lower cost project than anything else that it considers. It's got CLIC on its radar. It's got the Future Circular Collider, both of which are more than one order of magnitude higher in cost than the LHeC. So depending on how the CERN budget looks, you would first of all need a CERN management recognition that this should be part of its program, and then I think we start to look at it. But I think I agree with you, Rick, if your point is that the further forward it gets in time and the smaller the overlap with the high luminosity LHC, the less value there is in it for the CERN program.
Okay, so I have a comment. I think I agree with you that one of the great points, at least from the point of view of CERN, is that this is probably the cheapest Higgs factory that you can possibly imagine. And to me, the E plus E minus always sells the complete kinematic constraint that you get with the E plus E minus machine as a Higgs factory. And the kinematic constraint because you have E plus E minus, right?
Mm-hmm. Yeah.
So those of us that work at Hera know how valuable the longitudinal kinematic constraint at EP machines are.
Mm.
And so I think you get almost 90% of the kinematic constraint that you get with E plus E minus. And I think you guys should make much more of that. I think that's a very visceral argument that people will understand why this machine is such a good Higgs factory. And I think that might be a line of argument that you might try.
Mm-hmm. Okay, thank you. I mean, I think that's that's built into the analysis, but maybe people should shout about it a little bit more because it's not present in PP. Yeah. Thank you.
Good. So this is a speculative question, Paul. So it's the same more or less if you show impressive plots of PDFs over large range. Rick just mentioned the impact more or less for the Higgs. Can you make a similar story for the top? I mean, nobody really has looked at F2 top at all. So in principle, you get plenty of top. So is there a direct impact you could make also from the top structure function for LHeC?
I'm not sure whether people have thought about it in quite that language. Top structure function. Yeah, why not? I mean, generated dynamically through boson-gluon fusion. I'm just trying to converge on the right page. I mean, there is the dominant top production mechanism is charge current single top, but there is also a TT bar production rate. So yes, I think that would certainly be interesting. I mean, whether you call it a top structure function, don't know.
Hi, Paul. Andrea.
Hello, Andrew.
I agree on the comments that have been made before. I'm trying to get to the frame in which you are moving. For me, it's a very interesting project. As I was said before, is the cheapest. It's 1.5 billions, probably, more or less, compared to the high energy, which is of the order of 5 billions, and on the FCC, which is of the order of more than 20. On top of this, if we think about the cost which will have to be made to dig 100 kilometers tunnel, which is about 4.5 billions. That is, as we say, the cheapest one. But you have to convince the community. So the money is limited. You have to have the community of the LHeC to come after you. How is going in that direction?
Mm-hmm. So
I think the second comment is that let's say CERN needs to start digging the tunnel at some point for the FCC if it wants to go in that direction. And the sooner the better, probably. That is another problem. Okay. Thank you.
Okay, so I think it's a nice comment, and I agree with you about the numbers. there is this ongoing European strategy exercise, which I think is where CERN expects to sort of get its next direction from. Papers are submitted by the end of this year, and by the end of next year or so, I think CERN will be making, the CERN Council, who runs it, will be making statements about that.
Hope so.
I mean, one would think that CERN needs to decide on what its next project is on the timescale of the next few years, and it's a very complicated question that also depends what happens in the Far East, for example, with E+E- machines. I don't think anybody's about to start digging tunnels just yet for FCC. Let's put it that way. I think there's, it's not even obvious to me that it's technically feasible yet.
Hi, this is Zenedine Meziani. My comment is the following. It's actually nice to see the simulations on the JSI and trying to discriminate between the different models of saturation. My concern, or at least my suggestion, would be to also look at the upsilon and first kind of control a little bit what's going on with the convergence of NLO corrections in terms of the interpretation of those curves, especially as we see that the differences could be as large as, you are in a region where differences could be quite large due to, NLO corrections. So I think having the JSI and the upsilon to do these comparisons and to look into the effects of saturation would be important. Thanks.
Thank you. I think that's also a nice comment. We have studied the upsilon, and we've got similar plots to this. The kinematics aren't quite so nice. Just because the mass is higher, you don't get to such low X. You're at slightly higher scales, essentially. But yes, one would like to also constrain things based on understanding what happens with upsilons. Yeah.
I have a question. Maybe I missed that, but one of the things we did in the EIC white paper as one of the possible saturation signals was plotting just sigma diffractive over sigma total, the ratio. And maybe I missed that in your slides. Have you guys looked at that? Because especially for a nuclear target, that would be a very striking signal for saturation, that the ratio would be much higher than otherwise expected.
Thank you. And yeah, I know the plot from the white paper. No, you didn't miss it in my slides. We thought about it and we need to do it, and it's on the list. But I think having an LHeC version of that plot would be a very good idea. Yeah.
And the other thing from the same white paper are digits and the correlation of the back-to-back azimuthal correlation. Just to throw some ideas out there.
The azimuthal correlations between...
looking at back-to-back jets.
Yeah, okay. So
back-to-back peak would be washed out if there are saturation effects, or at least would be reduced.
Yeah. So there were some studies of that, and in fact, I'm a little bit involved in Atlas analysis in heavy ions to do that sort of azimuthal decorrelation analysis as well. And yeah, it translates very nicely into LHeC physics. There are not too many people working at the moment on all of these things, unfortunately, but it's nice to have the shopping list.
I see. Thank you.
Right. I don't see any other questions, so let's thank Paul once again.
Thank you for joining us remotely. And the next talk will be given by Matthew Wing, who's going to talk about LHeC. So what you do is just